Today we're going to do Newton's third law. In other words, if I punch it, it punches me right back. Newton's third law is usually stated, every action has an equal and opposite reaction. But that's not about you dumping your crush and then getting dumped by the next person. The point is, if you exert a certain force on an object, that object will automatically exert an equal and opposite force right back on you. It comes with the territory. You can't push without being pushed. You push the object, you get the same number of newtons in the opposite direction right back on you. This is why anybody who knows anything about boats knows not to walk in them. You try to walk forward on a boat, great. That boat, which is not tied down and is free to move however it likes, will move right back the opposite way. You exert a force on it, it exerts a force right back on you. These forces are sometimes called action-reaction pairs. You exert a force on an object, that object exerts a force right back on you. In a minute, you'll try some action-reaction pairs. They're very straightforward. Before you start, please take the following notes in addition to what you had on the previous slide. Action-reaction pairs may have the same numbers, but not much else. If you exert a force on an object, it exerts an equal and opposite force right back on you. But those interaction forces act on different objects with different effects on different free body diagrams. Let's take a look. Take out your action-reaction pairs worksheet. Take 5 minutes, no more, to do all of the examples on the front. For instance, the first one is done for you. If you try to hit a wall with your fist, you will find that the wall hits your fist right back. Now, A, head bumps the ball. What also happens at the same time? Go through all 9 of these examples. If you have extra time before everybody else is quite done, find action-reaction pairs on the system down here with the strongman and the monkey and the tree and all those little spring scales in between. Press pause at this stage. In 5 minutes' time, when just about everybody is done, we are going to go over the answers Jeopardy style. Take it away. Okay, now that you've unpaused the video, we're ready to check your answers. Start in the left-hand corner of the room over by the sink. Go all the way around the room, going clockwise, each person with one answer. I'll ask the question, now you'll answer. Just read what's written on your page. Here's the question. A, you're up. Why can a soccer player badly hurt her head? Read exactly what's written on the page and describe how you're going to get a head injury. Pause. Ready? Now B. Here's the question for B. How can you damage your windshield by driving too fast? Pause. Read exactly what's on your page. That's right. If you hit that bug with 100 newtons worth of force, that bug hits you with 100 newtons worth of force right back. 100 newtons of force is going to be absolute bug Armageddon, as per the opening sequence of Men in Black. But yes, it also has the potential to make a nasty crack in your windshield. C. Why do baseball bats break? Why do you need to restring your Technics racket from time to time? C. Read what's written on your page, explain the physics of it all. Pause and go. D. The genie does this in Disney's Aladdin. It makes my skin crawl. How can you hurt your finger on someone's nose if you really try hard enough? Pause, read what you have for D. Now, this one a little nearer and dearer to my heart. If you try pulling weeds without garden gloves, you will not get rope burn. You will get something much, much worse. It's like rope burn, only it's green and it cuts. It's called weed burn. Why do you need to wear garden gloves? E, you're up. Read what's written on the page. Pause. That's right. Just as hard as your hand pulls that weed, your weed pulls right back. Yeah. All right. F. Now let's go for some comedy. Featherweight taco champion is not allowed in the heavyweight room. Why not? F. Pause, read what's written on your paper. G. How do balloon rockets work? Read what you have for G. Pause. Ooh, yeah, that one was an interesting one. The opposite of outward is inward. The compressed air pushes the balloon surface outward, so the balloon surface pushes the compressed air inward. Now, untie the knot, give that pressure someplace to go, and whoosh. What else can you think of? Pause, read some of your more practical and more interesting applications. Restart the movie when you're done. All right. Now, for the longest physics experiment of your life. It took you probably at least 10 or 11 months to finish this experiment, sometimes closer to a whole year. How'd you walk? Go on now. Figure it out. Pause. Try and give instructions. Let's see how well they work.
Your toes, and then you put your right foot down, and you take your left foot, and you put your left foot down, and shift your weight to your left foot.
Okay, I'm doing that.
Why are your feet off the ground?
I'm not going anywhere. Cut. There you go then. You can take steps and shift your weight and spin as much as you please, but there's one thing you need in order to walk more than anything else. What is it? Pause. That's right. It's the ground. If your feet aren't on the ground, you're not going anywhere. Now, check out the baby. The baby takes months and months to figure this out. How do you walk? You need to move forward. You have the ground to push on. Use Newton's law to figure out in 1 minute what it takes the baby months to work out. Pause, press play when you think you've got it, and you've got force that's going to push you forward. That's right. You have to push backward on the ground in order for the ground to push forward on you. My youngest daughter figured this out at about 11-ish, 12-ish months. She was just learning to crawl, and right in front of her on the floor was the toy. It was just out of reach, and she was learning to crawl. She got on all fours, and she pushed forward on the ground with all her might, and Newton's third law, the ground pushed backward on her, and she scooched back. And she's like, okay, all right, temporary setback. I can do this. I'm super baby. I will get that toy. I will get that toy. And she's trying to crawl, and she pushed forward on the ground, and the ground pushed backward onto her, and she got further back, and she kept trying this again and again, and she got further and further from the toy, and she finally sat down and burst into tears of baby frustration. I want the toy, but physics. And then, within a couple of days, she figured out, I get it. I push backward on the ground, so the ground pushes forwards on me, and forward we go. Now you gotta figure out how to do that on 2 feet, and we call that walking. Now with all this walkie practice, we should be doing great on how to swim. Pause the video. Take a quick survey. Probably got some swimmers in the room. How do you swim? Physics style, fundamentally. Press play when you're ready. That's right. It's easy compared to the ground. The whole point of swimming is that you push backward on the water so that the water pushes forward on you. Everything else is technique. If you've got a wall to push up on, so much the better. You push backward on the wall pushes forward on you, and forward you go. Why can't we do this as well as things like dolphins and porpoises and fish? You can't push a whole lot of water with these wiggly little things with the opposable thumbs. If you really want to push a lot of water back so that a lot of water pushes forward on you, hey, there's some fins, and you'll be able to push lots more water. Seems simple, right? What's the one thing you need in order to swim? Water. Now, let's try it again with how to fly. You want to fly up. We don't need to fly forward. Forward is running. We can do that. We've got the ground. But if you want to be in the air, what do you have to do? Shout it out. Go on. That's right. The whole art of flying is that you have to push downward on the air so that the air pushes up on you. Well, should be pretty good. For some reason, I am not lifting off. Let's throw a little bit of math into here. How hard do you have to push the air? Make a free body diagram for you trying to fly. Go on, free body diagram. Now, what's the first force everybody put on your free body diagram? Shout it out. That's right, it's gravity. How big is gravity? Your weight. Make an upward force on your free body diagram. That's the force of the air pushing up on you while you push down on it. All right, how big does that force have to be in order to get you off the ground? Shout it out. That's right, that force has to be bigger than your weight. Why is it that all my flapping is not doing anything? Because I am not pushing down on the equivalent of my weight in air. And think of how many kilos I weigh. That's a lot of air to push. Why is it that birds do this, but we can't? I call them bird brains for a reason. Not only are their bones hollow, which is a great saver in weight, they got these teeny tiny little bird brains with these teeny tiny little skulls. They may be dumber than a box of rocks, but they don't have all that extra weight that we are carrying around out here. Not just in the smarts and the bigger brains, but more importantly, the big, heavy skull that protects the clever brains from things like concussions and girls' soccer practice. Insects and birds can do this, but we can't because they are so much lighter than we are. Now let's add the fact that they have wingspan. I can stand like this, but my arm span is going to be insignificant compared to the size of my body. Look at these birds. Look at this wingspan compared to the size of its body. Now think of something like a dragonfly, which has got 4 of them. Think of insects whose wings are much, much bigger than they are. If we were to have enough wingspan to get us airborne, you could stand in the center of this classroom, and your wings would go from one corner of the room diagonally across to the other corner of the room. Oh, wait! Then you'd need muscles to power all those wings, and the muscles would be heavy, and we'd be right back where we started. People are never going to fly unless we use an airplane. How does an airplane work? An airplane is a big, giant engine that pushes the air down. How much air? We'll get a jet engine pushing, and you can push down significantly more air than the weight of your plane. Airplane wings are cut in a certain configuration. They are not flat. That was one of the first things the Wright brothers figured out, and Feng Zhou Gai, the Chinese-American pilot, learned from them. You need wing configuration. Flat wings like a paper airplane, not going to do it. The wings are cut diagonally along the width to create a low-pressure zone above and a high-pressure zone below, with the end result that the wings, as they cut through the sky at top speed, force the air down. And if the wings force the air down, that means the air forces the wings up. That's why airplanes need to take off at top speed. Other than that, this nice diagonal wing just sits there on the ground, not pushing anything. Helicopters do this with rotating blades. The blades cut the air on the diagonal this way. It's a lot harder to do, but it gives you much greater maneuverability. They push the air down, the air pushes them up. Now, review. What's the one thing you need in order to fly? Shout out. No, not the wings. Helicopters don't have wings. Try again. Think about what's the one thing you need in order to swim. Well, to swim you need water. To fly you need air. The one thing you need to fly is air. And that's why rocket science is proverbial for being so complicated. It's rocket science because there's no air. There's nothing to push on. You can't fly in space because there's no air. It's definitional. Air and space, as in the Air and Space Museum or the National Air and Space Association, are 2 completely different disciplines. How on earth can you fly in space if there's nothing to push on? If you're designing a jetpack to work in space, what should it do? Pause the video and shout out suggestions for 30 seconds for how you can find something in space to push on, and don't say the ground because please note, this is space. There is no ground. Pause. All right. I hope one of you said, bring your own air to push on. It's fundamentally the only thing we can do, practically speaking. Bringing a giant bag of air to space is going to be a little bit difficult. If it gets a hole in it, then that's the end of you. But maybe we can bring something a little more compact than air. Let's see, more compact than a gas, that would be a liquid or a solid. Maybe we can bring some fuel. And by burning the fuel, we can make very compact air, and we can push on it. The jetpack is there to take the place of the air. Get this. The business end of this jetpack is not the fire. It's the exhaust. You are bringing gas to space, not air, because air is real hard to compress, and who would want to anyway. You are bringing all the potential to make gas in the fuel that you're going to burn, and when you burn the fuel and you force it out the thrusters, you force the exhaust gases down, and the exhaust gases force you up. That is rocket science in one animation or less. Bring your own gas. If you want to go forward, you push the gas backward, it pushes you forward, and you